Okay, so we're going to look at the interval and radius of convergence again today, but looking at series, taking the derivative of series and also the integral of series in series notation or summation notation. Okay, so what we know is that, well, one thing about taking the derivative and integral of a power series is that when we take the derivative and the integral, we take the derivative with respect to x. Everything else is basically a constant, okay? So the other thing is that for each derivative or antiderivative of the power series, the radius and interval of convergence remain the same. So that's really nice. Once you find the interval of convergence for the original series, you know the interval and radius of convergence for the derivative and the antiderivative, but you have to look at the endpoints. So we still have to test the endpoints. There's a couple tricks, okay? When you're integrating, a bracket will remain a bracket. So if the endpoint started as a bracket, it will stay a bracket, okay? If it started as and then when we're differentiating, if your endpoint started as a parentheses, it'll stay a parentheses. So we only have to test some endpoints, okay? All right, let's do this. This is gonna take a while, so let's do this. Okay, we're gonna find the interval of convergence for f of x, f prime of x, f double prime of x, and then the integral of f of x dx. Okay, so we have the f of x is equal to the sum from n is equal to 0 to infinity of -1 to the n times x to the n plus 1 over n plus 1. We need to apply the ratio test to figure out our interval. Okay, so I have the next term. Okay, I'm not going to deal with the -1. So I have x to the n plus 2 over n plus 2 times the reciprocal of a sub n, which is n plus 1, over x to the n plus 1. Okay? And this has to be less than 1 for convergence. So, writing this out, we have the limit as n approaches infinity of, okay, since I'm trying to cancel x plus 1, I'm going to write this as x to the n plus 1 times one more factor of x over n plus 1 times n plus 1 over x to the n plus 1. You don't have to write it like that, but that's how I'm going to do it today. Okay, those cancel, leaving me with the limit as n approaches infinity of the absolute value of x times n plus 1. There should be a 2 in the denominator over n plus 2, okay, is less than 1. Okay. So when I apply the infinity, I can see I'm going to get infinity over infinity, but I also remember that this is an eats DC situation. So today I'm going to take the shortcut here and just say that I know that these n plus 1 and n plus 2 are really going to cancel each other out in terms of rate. So I just get the absolute value of x has to be less than 1. Let's split this absolute value into less than 1 and greater than -1. So x has to be less than 1 and greater than -1. So if I write this on a number line, the center is 0, and my interval of convergence is going to be from -1 to 1, but I don't know about the endpoints, okay? So my radius is equal to 1, the center is equal to 0, and then I'm going to get my interval of convergence by testing the endpoints. So we need to test the ends. We need to let x equal -1, and the series, just going to write it up here, the series is n is equal to 0 to infinity of -1 to the n times x to the n plus 1 all over n plus 1. Okay, so let's go ahead and plug in -1 in for x. I have the sum from n is equal to 0 to infinity of -1 to the n times -1 to the n plus 1 over n plus 1. This is a situation where the numerator is always going to give me one positive one and one negative one. So like they're just going to switch off like last time. So n is equal to, the sum from n is equal to 0 to infinity of the numerator will always evaluate to be a 1. And then, so it's negative 1 over n plus 1. Okay, so I like to use integral test here. So I'm going to end up with, I did this one yesterday. Okay, so 1 over x plus 1, because I can rewrite this as negative, the negative sum of n is equal to 0 to infinity of 1 over n plus 1. So I'm just going to evaluate this part, and then if I can, I'll multiply by the negative 1. So 1 over x plus 1 is positive, decreasing, and continuous on the interval, because it's only not continuous at x equals negative 1. So I have the integral from 0 to infinity of 1 over x plus 1 dx, which is the limit as b approaches infinity of 0 to b of 1 over x plus 1 dx. The limit as b approaches infinity of the ln of the absolute value of x plus 1 divided by 1 from 0 to b. So we get the limit as b approaches infinity of the ln of b plus 1, the absolute value of b plus 1, minus the ln of 1, which is going to give me negative 1 times infinity minus 0. So the series diverges by integral test. Okay, so going back up to our number line, at negative 1, we diverge. So let's go ahead and look at, we're going to let x equal positive 1. Okay, so we have the sum from n is equal to 0 to infinity of negative 1 to the n. Our x is positive 1 to the n plus 1 over n plus 1. Okay, this guy is always positive, so I'm just going to cancel it out. So I just have the sum from n is equal to 0 to infinity of negative 1 to the n over n plus 1. This is an alternating series. Alternating series are so much easier to deal with. So I have the limit as n approaches infinity of 1 over n plus 1, which is equal to 0. That's the first condition. Second condition is n plus 1 compared to n plus 2. N plus 1 is 1 over n plus 1 is greater than 1 over n plus 2. So the terms are going to decrease as time elapses. Okay, so the series converges by alternating series test. So again, going back to my number line, I have an included bracket on positive 1. So the interval of convergence would be from negative 1 excluded to 1 included, or negative 1 is less than x, which is less than or equal to 1. Okay, so that is the interval of convergence for f of x. Now we need to find the interval of convergence for f prime of x, f double prime of x, and the integral of f of x. Okay, so I'm just going to draw a line right there. Okay, so f prime, actually f of x is equal to the sum of n is equal to 0 to infinity of negative 1 to the n times x to the n plus 1 all over n plus 1. Okay, and remember we're gonna take the derivative with respect to x. So the n's are everything else is just a fixed number. It's just a constant. It's a parameter. Okay. So if I'm going to take the derivative of f of x, I get the sum from n is equal to 0 to infinity. Negative 1 to the n stays negative 1 to the n. Then I take the derivative of really just x to the n plus 1. So I multiply by n plus 1, which is the power, times x to the n, because I'm going to subtract 1 for the power, all over n plus 1 doesn't have an x, so it just stays an n plus 1. Okay, so this is my n plus 1s are going to cancel. So f prime of x is equal to the sum from n is equal to 0 to infinity of negative 1 to the n times x to the n. This right here is the series for the first derivative. It's just that, just like that. Now we have to find the interval of convergence. Okay, remember, the interval of convergence is the same as f of x. So it's going to be from negative 1 to 1. And any when I'm taking the derivative, any parentheses that I had before will stay the same. So since I had a parentheses around at negative 1, I'm going to put a parentheses around negative 1. It's going to stay excluded, basically. But I don't know what happens at x equals 1, so I need to test it. Okay, so I'm going to test x equals 1. So I'm going to have the sum from n is equal to 0 to infinity of negative 1 to the n times 1 to the n. So I'm just replacing this x with 1. So 1 to the n is always going to be positive. So I just have the sum from n is equal to 0 of negative 1 to the n. So I am going to use alternating series tests since this is going to alternate. So I have the limit as n approaches infinity of 1. And so I end up with, or 1 to the n, sorry, it's going to end up with infinity. So the series diverges by nth term test. Remember, if the first condition of alternating series fails, then you just diverge by nth term test. Okay, so that means that the bracket is going to turn to a parentheses there. So the interval of convergence for f prime of x is negative 1 to 1 excluded. All right, now we're going to do f double prime. Okay, so f prime of x is equal to the sum from n is equal to 0 to infinity of negative 1 to the n times x to the n. So if I want to take the second derivative, okay, negative 1 to the n stays the same, okay, times the derivative, really we're just taking the derivative of x to the n. So multiply by n, and then I get x to the n minus 1. That's cool. The other thing that is super cool is that the interval of convergence, remember, it's just going to continue to stay the same. So we end up with negative 1 to 1, and any parentheses is also going to stay the same. So we already had that the endpoints were excluded, so now they're just going to continue to stay excluded. So if I take the third derivative, the fourth derivative, the fifth derivative, the endpoints will continue to be excluded. Okay, what we need to do now is take the integral. We're going to take the integral of f of x dx. So that is going to look like the integral of, and then I better write f of x down, the sum from n is equal to 0 to infinity of -1 to the n times x to the n plus 1 over n plus 1 dx. Okay, so I can either write this like this, or I can write it as the sum from n is equal to 0 to infinity of the integral of -1 to the n times x to the n plus 1 over n plus 1 dx. Okay? Okay, we're almost done. So what we do is take the integral. So I end up with the sum from n is equal to 0 to infinity of, remember, really you're only taking the integral of anything with the x in it, so everything else is going to stay the same. -1 to the n, it's like a constant, plus 1 n plus 1 is in the denominator. And then to take the integral, we take x to the n plus, and we add a value. So instead of n plus 1, we're going to end up with n plus 2. And then we need to divide by that exponent, so n plus 2. And since this is an indefinite integral, another thing that we need to do is make sure we add on a constant. So c plus the sum. So we have the sum, and then we have some c value that we don't know where we're starting from at this point. Okay. All right. So we know that the interval of convergence is going to be -1 to 1. Remember from earlier that when we're integrating, any bracket is going to stay. So there was a bracket around -1. So we're going to keep a bracket around -1, but we need to figure out what's happening, or around +1. But we need to figure out what's happening at x is equal to -1. So we're going to test and let x equal -1. So I have the sum from n is equal to 0 to infinity of -1 to the n times, in for x is -1 to the n plus 2 over n plus 1 times n plus 2. Okay, so we simplify to give us, okay, n plus 2 and n are both going to be, they are basically equivalent. They're also either both going to be odd or both going to be even. So I can rewrite this as -1. I'll just rewrite it to the n times -1 to the n over n plus 1 times n plus 2. Okay. So, and then what I notice is that the numerator here is going to be really the same thing. It's to the 2n. So I'm either going to get a negative value and a negative value. So a negative times a negative, or a positive times a positive. So no matter what, I'm going to end up with, +1 in the numerator times n plus 1 times n plus 2. Okay. And I decided that I want to test this 1 over n plus 1 times 1 n plus 2 and compare it to 1 over n squared and see what happens. Okay. So what I have is that 1 over n plus 1 times n plus 2 is larger than, the denominator is larger, so it actually makes that fraction smaller. And if I draw that out, I'm like, okay, 1 over n squared is larger, and then 1 over n plus 1 times n plus 2 is smaller. So I know that the sum of 1 over n squared converges by p series, because p is equal to 2. And so if the upper series converges, then definitely the smaller series will also converge. So therefore the sum of 1 over n plus 1 times n plus 2 also converges by direct comparison test. Okay. So that means that this endpoint at -1 converges, so it gets a hard bracket. All right. I think that that's enough. So, yeah,